Every atom sitting in your body tonight was forged inside a star that died before our sun was even born. Not metaphorically, measurably. Scientists confirmed the origin of some of those atoms in 2017. Watching two dead stars collide 400 million light years away, and most people still don't know their own body is partly made of that collision. Exposed directly to the vacuum of space, a human being loses useful consciousness within 9 seconds. The lungs empty completely in about 12. And death, if nobody intervenes, arrives in under 2 minutes, while the body itself is only getting started with what happens next. Tonight, we'll go through what actually happens to a human body in the vacuum of space. Not the Hollywood version, but the real one. Why your blood doesn't boil the way every movie claims, why freezing takes far longer than freezing should, what happens to what's left of you if nobody ever comes home, and where your own atoms actually end up 1 billion years after everyone who knew you is gone. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. Here is the detail almost nobody gets right. A human body does not burst in the vacuum of space. Skin is strong enough, elastic enough, to hold everything inside it against the pressure difference. No window shatters, no rupture, no scene from a movie. What actually happens is stranger than an explosion, and far quieter. Not because the vacuum is gentle, because the failure it causes is invisible. And it starts on the inside, in places no camera would ever think to point. Does your blood actually boil the moment the air disappears? How many seconds of consciousness do you actually get before the dark takes you? Why does the cold take so much longer to arrive than every film assumes? What happens to what's left of you if no one ever comes back for it? And 1 billion years from now, where do your own atoms actually end up? Those 5 questions are the shape of tonight. Each one gets answered roughly in the order your body would actually experience them. Nothing about you would explode. Something quieter would happen instead. Hold that for a moment. A body, in the first fraction of a second of true vacuum, is not being attacked from outside. It is discovering, for the first time in its life, that the pressure it always pushed outward against was never matched by anything pushing back. Every breath a person has ever taken assumed an atmosphere pressing inward just enough to make breathing, circulation, and the shape of an eye possible. Remove that assumption, and the body does not detonate. It expands, unevenly, into the space where resistance used to be, not because the vacuum reaches in and tears it apart, because the atmosphere was never truly outside the body at all. It was load-bearing, and nobody notices a load-bearing wall until it's gone. Moisture on the tongue is the first thing to change. Not the organs, not the blood, not yet. The exposed, wet surfaces. Eyes, mouth, the lining of the lungs, if the one mistake that costs people the most gets made. Begin to do something that has nothing to do with heat and everything to do with pressure. Water does not need to be hot to boil. It needs only for the pressure holding it liquid to disappear. And in true vacuum, that pressure is gone completely, all at once. That single fact rewrites almost everything the movies ever told you. The danger was never fire. It was the absence of a number most people have never thought about in their entire lives. The number that keeps water, liquid instead of gas, sitting behind every glass you have ever filled. You have felt a distant cousin of this pressure your entire life without noticing it. The faint pop in your ears on a descending flight, the mild ache in a sinus during a fast elevator ride. Those are tiny, survivable rehearsals of the same principle. Pressure shifting around a body built to expect one specific number, and only that number. Multiply that shift by the full weight of an atmosphere. Remove it entirely instead of nudging it, and the rehearsal becomes the real event. 14.7 pounds of pressure pushing on every inch of a body all day, every day, so constantly that almost nobody ever consciously registers carrying it. It is not background noise. It is a structural assumption built into every cell membrane, every capillary wall, every drop of fluid held exactly where it is supposed to be. We'll come back to what that means for blood specifically, because the answer is not what you expect. But first, there is a clock already running, and it is shorter than almost anyone assumes. Forget minutes. Forget the slow-motion countdown of a film score. From the instant true vacuum surrounds an unprotected human body, the useful, thinking part of you has somewhere between 9 and 11 seconds left, a number pulled not from speculation, but from real high-altitude decompression research. And from the handful of accidents that gave scientists data nobody wanted to collect this way, 9 seconds is barely enough to finish reading this sentence aloud. The mechanism is almost insultingly simple once you know it. Blood carries oxygen to the brain under pressure, and it takes only a few seconds. Once that pressure collapses, for the blood already inside your skull to stop delivering anything useful at all. Your brain does not run out of oxygen the way a candle runs out of wax. Slowly, visibly. It runs out the way a phone loses signal in a tunnel. Instantly. Completely. With no dimming in between. Pilots training for high-altitude ejections learn this number by heart, because at extreme altitude the air itself is thin enough to approximate the same collapse, without ever leaving the atmosphere. The consciousness clock in a fighter jet cockpit above 60,000 feet and the consciousness clock in the open vacuum of space are, for a few critical seconds, telling nearly the same story. And yet the body does not simply switch off like a light. There is a specific, well-documented sequence. A narrowing of vision first, the way a room seems to shrink at the edges, then a loss of coordinated movement, then unconsciousness. The entire sequence compressed into a window shorter than most people take to tie a shoelace. After consciousness goes, the body does not stop working immediately. The heart keeps beating for a short while longer, moving blood that can no longer do its job, the way a pump keeps turning after the well runs dry. Cardiac arrest follows within roughly 90 seconds to a few minutes, depending on the individual and the exact conditions. The true, final boundary between exposure and death, assuming nothing intervenes. And this is where it stops matching what most people assume. A person exposed this way is not necessarily in pain during those 9 seconds. There is no time for the nervous system to organize something as complex as suffering. What there is, instead, is a kind of falling, vision narrowing, sound fading, the world closing like a door pulled shut by someone standing just out of sight. Researchers call this figure the time of useful consciousness, and they have measured versions of it for decades using altitude chambers, never true vacuum, because true vacuum leaves no room for a second attempt. At the equivalent of 25,000 feet, useful consciousness lasts a few minutes. At the equivalent of 40,000 feet, it collapses to under 20 seconds. Push the number all the way to true vacuum, and it bottoms out at 9, the floor beneath which the body simply has no more room to fall slower. Now consider what that number actually buys a rescuer. 9 seconds is not long enough to unbuckle a harness, cross a room, and seal a hatch. It is barely long enough to notice something has gone wrong at all. Every design decision behind a real spacecraft's emergency procedures, the placement of manual override switches, the speed of automatic pressure alarms, exists because of this single, unforgiving number, 9 seconds. That is the entire window in which a rescue, a repressurized suit, or a sealed hatch changes everything. Past it, the story stops being about saving a person and starts being about something the human body has never had to do naturally in 4 billion years of evolution. Exist, indefinitely, in a place with no air at all. Here is the reframe that should have come first, and didn't, because Hollywood needed a better visual. Your blood does not boil in space. Not because the physics is wrong, because your circulatory system is sealed, elastic, and still under enough of its own internal pressure to keep blood liquid, at least for a meaningful stretch of time. What boils is something else entirely, and it happens almost instantly. Saliva on your tongue, tears in your eyes, if they're open, the thin moisture lining any exposed mucous membrane. These surfaces have no skin to protect them, no elastic barrier holding a pressure difference at bay. They are directly exposed to true vacuum and water at body temperature. With no pressure pushing back on it, boils at a temperature far below what your body normally runs. Scientists call it ebullition, a word that sounds almost gentle for what it describes. The spontaneous vaporization of the water inside living tissue. The moment external pressure collapses far enough, picture a sealed water bottle at altitude, the kind that puffs up on a plane during ascent, straining against its own cap. Now remove the cap entirely, in a vacuum instead of thin air, and let that pressure difference go all the way to zero. That puffing, straining reaction, stretched to its absolute limit, is closer to what happens to your exposed tissue than anything resembling fire. Not fire, not burning, a cold, mechanical unsealing of water from its liquid state, driven by pressure and nothing else. Skin changes this story completely, and this is the part that surprised the scientists who first studied it. Underneath intact skin, the body's own elasticity provides enough counterpressure to keep deep tissue and blood from boiling outright. The skin acts as a kind of pressure vessel, holding the body's internal environment together even with nothing pushing back from outside. Swelling happens. Documented cases and animal studies show tissue expanding to roughly twice its normal volume, within seconds, a visibly puffed, waterlogged look. But the body does not burst, and blood contained within intact vessels does not immediately vaporize the way exposed saliva does. This is where the Hollywood image and the real one diverge most sharply. The exposed surfaces suffer first and fastest. Eyes, mouth, throat, while the sealed elastic majority of the body buys itself a strange kind of borrowed time, ballooning rather than bursting, holding its shape a little longer than anyone watching a movie would expect. Scientists confirmed most of this decades ago, using a mix of animal research and a small, unsettling collection of real human accidents, decompression events in high-altitude test chambers, and at least one incident inside NASA's own vacuum test facilities that nobody scripted and nobody wanted repeated. Much of what physiologists know about the timeline came from US Air Force research in the 1,960 seconds, exposing anesthetized animals to near vacuum for carefully measured intervals and documenting exactly what recovered afterward and what didn't. Subjects exposed for under roughly 90 seconds and then repressurized survived, often with no lasting harm at all once swelling subsided. Past about a minute and a half, the outcome shifted hard toward fatal, and no amount of subsequent care reversed it. Pause on that number. 90 seconds is not a metaphor for how briefly this window stays open. It is closer to a measured, repeatable boundary. A hinge between an incident and a fatality, sitting almost right where a person's own held breath would have already done its worst. In 1965, a NASA engineer named Jim LeBlanc was testing a prototype spacesuit inside a vacuum chamber in Houston when a hose connected to his suit came loose. The chamber had already been pumped down to a near vacuum, simulating the environment above roughly 100,000 feet, not the true vacuum of open space, but close enough that his body responded almost the same way physiologists would later confirm actual space exposure behaves. LeBlanc later described the last thing he remembered before losing consciousness: the saliva on his tongue beginning to boil, a strange, specific sensation, oddly free of pain or panic, of the moisture in his mouth turning to vapor, and then nothing. He was unconscious within roughly 14 seconds. close enough to the theoretical number that his case became one of the most cited data points in high-altitude physiology, precisely because almost nobody else who has been exposed this way lived to describe what it felt like from the inside. A technician in the control room noticed the pressure alarm and made a decision that saved LeBlanc's life. Instead of following the slower standard procedure to properly repressurize the chamber, he manually flooded it with air as fast as the system allowed. LeBlanc regained consciousness around 12 to 15 seconds after air began returning, reporting no lasting injury from an exposure that, extended by even another minute, models suggest would have been fatal. Here is what almost nobody considers about his account. He never once described heat. Not burning, not fire, nothing resembling the space exposure scenes populating decades of science fiction. What he described was pressure leaving, moisture-changing state, and a narrowing of awareness that felt, in his own words, less like an attack and more like a light being turned down. LeBlanc returned to work at NASA not long after, and by his own account, carried no lasting fear of the suits he had spent his career testing. What changed was procedure, not personnel. The incident became a training case study, cited for decades afterward, part of the reasoning behind requiring at least 2 technicians monitoring any human vacuum test from that point forward, one of them with a hand permanently on the emergency repressurization control. Engineers who worked alongside him later said the episode changed how carefully every hose fitting on every subsequent suit was checked, twice, by 2 separate people, before any chamber was ever sealed again. His case remains one of the only first-hand human descriptions of real, near-vacuum exposure and survival on record. And it exists because one technician chose speed over protocol. In the same 14 seconds physiologists now use to explain exactly what you would feel if it ever happened to you. But LeBlanc had one advantage that changes this entire story completely. Someone was watching, and air came back. What happens to your body if vacuum keeps it? With nobody left to flood the chamber, is the question the rest of tonight actually answers. Every instinct a human body has ever developed says the same thing in an emergency. Hold your breath. It is the single response drilled into swimmers, divers, and anyone who has ever gone underwater since infancy. In the vacuum of space, it is the one instinct that turns a survivable few seconds into a fatal one. Here is the mechanism, and it is pure, unforgiving physics. Gas expands as pressure drops. The same principle that makes a bag of chips puff up on an airplane at altitude. Your lungs are full of gas. If the airway stays open, that air simply rushes out, fast but harmlessly, following the pressure down. If you seal your throat and hold it in, the same expanding gas has nowhere to go, and lung tissue is not built to contain a pressure difference that extreme. It tears. Air forced through torn lung tissue does not just escape into the chest cavity. It can enter the bloodstream directly, forming bubbles that travel wherever blood travels, including straight to the brain and heart. Physicians call it an arterial gas embolism, and it is capable of causing a stroke or cardiac arrest within seconds, faster than straightforward hypoxia would ever kill on its own. Now add the cruelest part of the mechanism. This is not a rare edge case. It is the single most emphasized rule in every high-altitude and hyperbaric training program on record. Repeated specifically because the instinct to hold your breath is so strong that people have to be drilled over and over to override it. Military air crews training for rapid decompression are taught one command above all others: exhale, and keep exhaling all the way down. Scientists studying decompression injuries in animal models found the same result again and again. Subjects whose airways were held closed suffered severe, often fatal lung damage within moments, while subjects whose airways stayed open, breathing freely outward, sustained comparatively little internal injury even at full vacuum exposure. The difference between the two groups was not the vacuum. It was one open airway, a closed throat, In other words, is more dangerous to a human body in this scenario than the vacuum itself. The environment that seems to demand you hold on, brace, protect the air already in your chest, is the one environment where doing that will kill you faster than anything else in the room. Submarine escape training runs on the identical principle. For the identical reason, sailors ascending from a disabled submarine are drilled to exhale continuously the entire way to the surface because the same expanding gas mechanism threatens their lungs during a rapid pressure change measured in mere tens of feet of water. Space simply applies the same lesson at a scale the human body has never been built to encounter on its own. Not a few atmospheres of difference, but the entire atmosphere, gone at once. And yet the fix costs nothing physical at all. No equipment, no drug required. Survival, in this one specific window, depends entirely on doing the opposite of every instinct a frightened body has ever formed. Letting go completely of the one thing every cell in your chest is screaming at you to hold on to. Lungs are not the only place gas hides inside a human body, and every other pocket of trapped air follows the same rule, just with lower stakes. The gas already sitting in your digestive tract, produced by ordinary digestion, ignored entirely until pressure stops holding it in check. Each of these pockets expands the moment external pressure drops, the identical mechanism driving the danger in your lungs, just distributed across smaller, less critical spaces. Ears may rupture. Sinuses can ache sharply enough to double a person over, even in a slow, controlled decompression at far gentler pressure changes than true vacuum. The gut, meanwhile, becomes almost comic by comparison to everything else happening to the body. Bloating, sometimes dramatically, as trapped intestinal gas expands with nothing to hold it back. None of it, on its own, is likely to be fatal. Ear and sinus barotrauma is common enough that pilots and divers train for it specifically, treating it as a painful nuisance rather than a life-threatening event. But here's the part that rarely gets said out loud. The body is not one sealed system reacting to vacuum as a single event. It is dozens of small, semi-independent air pockets, each following the same law of expanding gas, each on its own private timeline of minor rupture and pressure release. There is something almost absurd hidden inside this otherwise grim inventory. Somewhere in the same fraction of a second that a person's vision is narrowing and their consciousness is failing, their stomach is also, silently and mechanically, an indignity almost too small to belong in the same story as the rest of what's happening. Physiology rarely bothers to be dramatic about every detail at once. Some of it is simply gas, doing what gas does when nothing holds it back. Divers know a milder version of this well. Ascend too quickly from even a shallow dive and trapped air in a sinus or a filled tooth can cause pain sharp enough to stop a trained professional mid-swim at a pressure change vastly smaller than the one a body in space would face in an instant rather than over several careful minutes. Aviation medicine has documented ear and sinus barotrauma so extensively that it has its own specific treatment protocols, entirely separate from anything related to oxygen or cold. Hold that for a second. A single moment of exposure does not happen to your body once. It happens to your lungs, your ears, your sinuses, and your gut nearly simultaneously. Each pocket of trapped air discovering, independently, that nothing is pushing back on it anymore. And yet, of every pocket in the body, only one truly threatens to kill on its own within seconds. The one connected directly to the bloodstream, the one every training program drills you to keep open, no matter what your instincts scream at you to do instead. Every other pocket simply aches, swells, or empties. A body renegotiating its own geometry with no say in the matter at all. Cross off the ice statue image completely. It is, of every myth about dying in space, perhaps the most confidently wrong. Freezing solid, in the way frost forms on a windshield, requires something specific that space does not actually provide in the way people assume, a medium to carry heat away quickly. Air does that job on Earth. Through convection, cold molecules constantly bumping against your skin and carrying warmth off with them. Vacuum has no molecules to bump against anything. There is nothing there to touch you, cold or otherwise. Heat can only leave a body in vacuum through radiation, the same slow process by which a campfire's embers cool overnight, or through the direct evaporation of any remaining surface moisture. The same ebulism already stealing your saliva and tears in the first fraction of a second. Radiative heat loss is real, but it is dramatically slower than the conductive cooling most people imagine, because there is no surrounding cold substance actively stealing warmth away. Not because your body somehow resists cold in a vacuum, because cold, in the everyday sense of something cold touching you, does not exist in a vacuum at all. And this is where the cold space assumption stops making sense entirely. A body facing direct, unfiltered sunlight in space does not cool. It can overheat. The same raw solar radiation that warms a spacesuit's sun-facing side without any atmosphere to filter or scatter it first. Meanwhile, the shadowed side of that same body, at the very same moment, radiates its own heat away into the cold of open space. Slowly, unevenly, one side of a single exposed body running two different thermal stories at once. A NASA-era estimate for objects in low Earth orbit puts full surface cooling, in shadow, on the order of hours, not seconds. A number that would strike anyone raised on the frozen astronaut trope as almost absurdly slow. The core of the body, insulated by its own tissue, would take considerably longer still. Forget the frozen statue entirely. A body in space does something stranger and slower than freezing. It drifts, unevenly heated and unevenly cooled, holding onto its own warmth for far longer than anyone watching a movie would ever guess, while the moisture already lost to vacuum leaves the surface drier than any desert on Earth has ever made anything. Consider what that unevenness would actually look like, held still and watched for an hour. One shoulder catching raw sunlight, warming past anything comfortable. The other, in its own shadow, bleeding heat into the dark at the unhurried pace of an ember, losing its glow long after the fire is out. Nothing resembling a blizzard, nothing resembling visible frostbite spreading across skin. Just two temperatures coexisting on a single motionless body, refusing to average out for far longer than intuition allows. Spacesuit engineers design around this exact asymmetry every day, layering reflective coatings and heaters into suits, precisely because the sun-facing and shadow-facing sides of an astronaut's own body would otherwise drift dangerously far apart in temperature within a single working shift, outside a spacecraft. Here is everything settled so far, and it is essentially everything most people ever ask. The body does not explode, the blood does not boil the way the movies claim, and the ice statue image is close to backward. A body in the vacuum of space loses consciousness within 9 seconds, loses its life within minutes, if nothing intervenes, and does none of it the way a single film has ever depicted it. That much, physiologists have understood for decades, mostly from animal research, a handful of survived accidents, and the unglamorous mathematics of gas and pressure. That is the answer almost every article about dying in space settles for, and it is a real, complete, correctly researched answer. It is also measured against the actual question the title of tonight's episode asks, only the first layer of it. The part of the story small enough to fit inside a single human lifetime of attention. The part every article stops at, satisfied, as if the story ended where the heartbeat did. It doesn't. A body does not vanish the moment it stops living. It remains in an orbit, on a trajectory, inside a suit, or entirely without one, and vacuum keeps doing something to it for far longer than any of us are built to intuitively imagine. Days, years, spans of time that make the 9 seconds of consciousness look, in retrospect. Now add what actually happens once the medical emergency is over and the body simply continues existing, unrescued, in an environment that does not decompose things the way Earth does. Whether that body eventually burns up in an atmosphere within a few short years, or drifts, essentially unchanged, for spans of time longer than our entire species has existed, depends on one detail decided in the first moments after death: altitude, and nothing else. A body left in a low, decaying orbit is on borrowed time, measured in single-digit years. A body released on a trajectory that never comes back is on no clock at all. It could still be drifting, recognizably itself, after every person who ever knew its name has been dead for longer than civilization has existed. Between those two extremes sits every far stranger fact tonight still owes you. How a body without bacteria or moisture stops rotting and starts mummifying instead. What centuries of sunlight and dust actually do to it, and where, if nothing ever interrupts the process, its own atoms are already scheduled to end up regardless of what happens to it in space at all. What actually happens to what's left of you once the part of this that resembles a medical emergency is finished is a far stranger story than anything covered so far, and it is the one almost nobody ever tells. It starts, appropriately enough, with the single organ that was working hardest in those final 9 seconds, and what happens to it in the minutes right after it stops. Nothing about you would be destroyed. Something would simply change state. And the first thing to change, after the heart finally stops, is the one organ that spent its entire existence demanding more oxygen than any other part of you. The brain is a greedy organ by design, consuming roughly 1/5 of the body's total oxygen despite being a fraction of its total weight. Starve it, and the consequences begin almost immediately. Within 10 to 20 seconds of blood flow stopping entirely, electrical activity across the brain collapses, the same collapse doctors look for on a flatlined monitor. Within 4 to 6 minutes at normal body temperature, the damage to neurons becomes irreversible. A threshold emergency physicians treat as close to sacred the entire foundation of how long CPR is considered worth attempting. But here is where a body in the vacuum of space quietly breaks from a body that simply drowns or suffers a heart attack on Earth. Cold slows metabolic demand, and while true vacuum cools a body far more slowly than fiction assumes, the fastest cooling tissue is often the fastest exposed tissue too. Skin, extremities, the surface of the brain itself through thin bone, given enough time and the right orientation to open space. Emergency medicine has a name for the phenomenon in an entirely different context. Therapeutic hypothermia, deliberately cooling a patient's body to buy the brain extra minutes it would not otherwise have. That does not save anyone in space. No rescue arrives faster because the body cools a little. And 9 seconds of consciousness was never negotiable, but it changes, in a small and clinically real way, what already gone actually means at the cellular level, stretching the boundary between reversible and irreversible by minutes that, in this specific and unrescuable scenario, change nothing about the outcome and everything about how slowly the body arrives at it. Now layer in what is actually happening at the level of a single cell during those minutes. Without oxygen, cells cannot generate the molecule, adenosine triphosphate, the basic unit of biological energy. That keeps their internal machinery running. Sodium and calcium, normally kept carefully outside and inside specific membranes, begin leaking across boundaries they are never supposed to cross. Enzymes that should stay dormant activate and start breaking down the very structures they once helped maintain. None of this requires an outside observer to notice. It happens in the dark, inside tissue that will never again receive a signal telling it to stop. Emergency medicine draws its 4 to 6 minute line precisely at the point where enough of this cellular unraveling has occurred that restarting the system, even with a beating heart and full oxygen restored, no longer restarts the person who owned it. In space, with no restart ever coming, that line stops mattering in the way it matters in a hospital. It becomes, instead, simply the moment the body finishes becoming what it will remain for a very long time afterward. By the time every electrical signal in the brain has finally gone quiet, ordinarily a matter of minutes, the body has already crossed from a medical emergency into something else entirely. a physical object, still warm in places, still recognizably itself, that the universe is now the only remaining party responsible for. On Earth, a body left exposed begins decomposing within hours, driven almost entirely by bacteria already living inside it, digesting from the inside out the moment the immune system stops holding them back. It is one of the most reliable biological processes on the planet. So reliable that forensic scientists use its exact stages to estimate time of death down to the hour. None of that happens in space, and the reason has nothing to do with cold. Bacteria need liquid water to function, and the same vacuum stealing moisture from your tongue and eyes in the first instant keeps stealing it from every exposed surface of the body for as long as any moisture remains to take. Within a surprisingly short span, hours to a few days, depending on the body's orientation to sunlight, a body in true vacuum would lose enough surface moisture that the bacteria responsible for ordinary decomposition would have nothing left to survive on. What replaces rot is closer to a process museums use on purpose: freeze drying, technically called lyophilization, where water is removed from tissue directly, without ever passing back through a liquid state. Food scientists and conservators use a controlled version of this same vacuum and cold combination to preserve things indefinitely: fruit, vaccines, even organ tissue for research, dried from the inside without ever rotting first. Your own body in vacuum would undergo an uncontrolled version of the same process. Your skin would draw tight against bone, soft tissue would harden rather than liquefy. Within months, a body that would have been unrecognizable bone and residue on Earth could instead look, structurally, almost like a dried, leathery cast of the person it once was. Not preserved out of mercy, but simply because nothing in the environment was left that knew how to make it decay. The timeline depends heavily on one detail: which side of the body faces the sunday. A surface in constant sunlight loses its remaining moisture faster, sublimating directly from solid ice crystals within cells into vapor that vacuum immediately carries away, leaving nothing behind to refreeze. A surface locked permanently in shadow, meanwhile, may hold on to trace ice for considerably longer. Effectively freeze-locked rather than freeze-dried, the same distinction food scientists rely on when deciding whether to sublimate a product quickly under a lamp or slowly in a cold, shielded chamber. Either path arrives at roughly the same destination eventually: a body with essentially no liquid water left in it at all, existing in a kind of preservation nobody designed and nothing intended, purely because the specific combination of cold, dryness, and absent microbial life happened to align. Weight itself would shift considerably in the process. The human body is roughly 60% water, and losing the majority of that mass to vacuum would leave behind something startlingly light for its size: a husk rather than a corpse in the ordinary sense of the word. And yet mummification is not immunity. It is only the first of several very different things a vacuum does to a body over time, and the next one has nothing to do with moisture at all. Take away the atmosphere, and you take away Earth's entire radiation shield along with it. No ozone layer filtering ultraviolet light, no thick blanket of air scattering and absorbing the harshest wavelengths the sun throws off every second. A body exposed to direct sunlight in space receives the full, unfiltered dose, and it starts working on that body immediately, long before anyone would think to call it damage. Astronauts on spacewalks wear visors and suits specifically engineered to block radiation levels that would blister unprotected skin within a single shift outside a spacecraft. Remove the suit, and ultraviolet light begins breaking down the molecular bonds in skin and exposed tissue within minutes, not years. The same mechanism behind an ordinary sunburn, simply operating without any atmosphere left to take the edge off first. But ultraviolet light is only the beginning, and arguably the gentlest part of it. Cosmic rays, high-energy particles flung out by distant supernovae, and the sun's own violent outbursts pass through unprotected tissue constantly on Earth too, just in far smaller numbers, filtered by miles of atmosphere and a planetary magnetic field doing quiet, thankless work over your head every day of your life. Without either shield, that bombardment continues at a much higher rate, steadily damaging the molecular structure of whatever remains of the body, one high-energy particle at a time. Scientists studying radiation exposure for future Mars missions have measured this directly. Astronauts outside a shielded spacecraft absorb a dose of cosmic radiation many times higher than anything permitted on Earth, high enough that mission planners treat total lifetime radiation exposure as one of the hardest limits on how long any astronaut can safely work in deep space at all. A body no longer protected by even a spacesuit, exposed indefinitely, receives that same bombardment without any of the limits designed to protect a living person, because there is no longer a living person left to protect. At the molecular level, radiation like this breaks chemical bonds directly, snapping strands of DNA still present in preserved tissue, scrambling proteins that would once have told a cell exactly what shape to hold. None of it requires life to continue happening. A dried, sun-bleached, radiation-etched shape can persist in this slow disassembly for a very long time, changing constantly at a scale too small to see, while looking, from any reasonable distance, almost the same year after year. Color would go first, in a sense, pigments in skin and hair breaking down chemically under constant ultraviolet exposure. The way a flag left flying for years eventually bleaches to a shadow of its original color, except with nobody around to ever take it down or replace it. None of this rots anything, and none of it happens instantly. It is closer to erosion than decay, a slow, relentless disassembly at the molecular level, running for as long as the body remains exposed, whether that turns out to be years or, on some orbits, far longer than years. In November of 1957, the Soviet Union launched a stray dog named Laika aboard Sputnik 2, the second object humanity ever placed in orbit. For over 40 years, the official story told to the public was a comforting one. Laika survived comfortably for about a week, sustained by food and oxygen, and was painlessly euthanized before her supplies ran out. A quiet, dignified end to a groundbreaking mission. In 2002, a Russian space agency scientist named Dmitry Malyshenkov finally released the true telemetry. Laika died within hours of launch, not days. The spacecraft's thermal control system had failed, and internal temperatures climbed rapidly beyond safe limits during only the fourth orbit. She died from overheating and stress, not from a planned, painless procedure. The comforting version had been a fabrication maintained for over 4 decades. Here is the detail that connects her story directly to the physiology already established. The failure that killed her was not the vacuum outside her capsule, it was heat, trapped inside a sealed vessel with nowhere to radiate away fast enough. The mirror image of a body's slow, uneven cooling in open vacuum, and a reminder that sealed spacecraft face their own separate thermal danger entirely, one that has nothing to do with freezing at all. Malyshenkov, decades later, said publicly that the program had learned less from her death than it should have, and that the true telemetry should never have been hidden as long as it was. It is a rare thing in the history of any space program for a scientist to say so plainly that an official story was wrong, on the record, in front of the public that had believed the original version for most of their lives. Consider what the two versions of her story actually reveal. Set side by side, the comforting version described a controlled, humane ending engineered on purpose by people who cared what happened to her. The real version described a thermal system nobody had fully tested for a mission this long, failing quietly, with no one aboard able to report that anything had gone wrong. Spacecraft, then and now, are not simply vessels for surviving the vacuum outside them. They are just as often fighting a second, quieter battle against the heat that has nowhere to go once trapped inside a sealed hull. Sputnik 2 itself, carrying her body, continued orbiting Earth for a little over 5 months after launch, slowly losing altitude to the faint drag of the outermost atmosphere before finally burning up on re-entry in April of 1958. Her body never returned. It simply kept circling, already gone, for a span of time longer than the entire mission had been designed to last. A real, documented answer to a question tonight will return to more than once. Exactly how long a body actually remains in an orbit like that before the orbit itself decides the ending. Now add the detail that makes her case more than a historical footnote, and the first one that applies directly to you. Sputnik 2's orbit was considered low even by the standards of 1,957, decaying within months precisely because enough thin atmosphere still existed at that altitude to drag against it. One faint collision at a time, until height itself ran out. Your own fate, on a similar orbit, would follow the exact same clock. Every physical detail already established about your own body in this exact scenario: the boiling saliva, the intact skin, the absence of any explosion, rests on a small foundation of real, tragic, documented human cases. And the most complete of them all happened in June of 1971 aboard a Soviet spacecraft named Soyuz 11. Cosmonauts Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev had just completed a record-setting 3 weeks aboard the Salyut 1 space station, the first crewed space station in history. Their capsule undocked and began its normal descent procedure back toward Earth. They did not die because the capsule depressurized violently. The way fiction usually stages this exact scenario, they died because a single valve, designed to open only after the capsule reached a safe, low altitude during final descent, released far too early, at an altitude still high enough to be, functionally, the vacuum of space. Investigators later determined the entire capsule's air escaped through that one small valve in under a minute. None of the 3 cosmonauts had time to reach the manual override before consciousness left them. Ground control had no way to know anything had gone wrong until the capsule landed on schedule, appearing entirely normal from the outside, its crew already gone. Autopsies confirmed, with a precision no simulation ever could, nearly every detail already established. Nitrogen bubbles were present in their blood, consistent with the pressure collapse. There was hemorrhaging in tissue exposed to the pressure change. And there was no explosion or rupture. Nothing resembling a single scene from a film. 3 bodies, found exactly where they had been sitting, entirely intact. Before Soyuz 11, decades of physiological modeling and animal research had produced a confident, well-reasoned prediction of what a real human decompression death would look like. The autopsy report did not overturn that prediction. It confirmed it, point by point, in circumstances nobody involved in the research had ever wanted realized. That distinction matters more than it might first appear. Everything tonight has described so far was, until June of 1971, still technically a well-supported theory. After that day, it became documented fact, carried at a cost no scientist would ever have chosen to pay for the data. They remain, to this day, the only human beings confirmed to have died from decompression in the vacuum of space. Their deaths led directly to a design requirement that every cosmonaut since has followed without exception: a pressure suit worn during launch and re-entry, specifically the 2 phases of any mission where a valve, a seal, or a single point of failure has the least amount of time to be caught before it becomes fatal. Their capsule, unlike Sputnik 2, did not remain in orbit. Soyuz 11 completed its automated landing on the steppe of Kazakhstan. Intact, on schedule, its 3 occupants already gone. A body's fate, in this one specific and terrible case, decided not by years of orbital decay, but by a single valve and a single minute that nobody watching from the ground had any way to see coming. Your own fate, sealed inside a capsule instead of a suit, would hinge on exactly that same kind of margin. Strip away the tragedy for a moment and look only at the mechanism. because the sequence itself is a case study in how quickly small failures compound into total ones. The descent module separates from the rest of the spacecraft exactly on schedule, a routine explosive bolt release performed on every mission before it. This time, the shock of separation jars loose, a valve never designed to open until much later in descent, at a much lower, safer altitude. The valve begins venting cabin air into vacuum immediately. Nobody sees it happen. There is no alarm loud enough, no light bright enough to outrun what is about to occur, because the capsule's own sensors were never built to expect a leak at this specific stage of flight. Cabin pressure begins falling within seconds. Air rushes toward the open valve, faster than any cabin system was ever designed to replace it. The pressure drop crosses the threshold at which useful consciousness begins its own countdown, the same 9 to 15 second window your own body would face, now unfolding for real, inside a spacecraft its crew had trusted completely just moments before. The crew, strapped into their seats for landing, reach for the valve. Investigators later found it had, in fact, been located and gripped, but by then, hands were already losing the coordination needed to turn it, the same narrowing of motor control that precedes unconsciousness in every documented case of rapid decompression. Seconds mattered more than strength ever could have. Meanwhile, the capsule itself notices nothing wrong. Trajectory holds steady. Descent continues on schedule. The automated systems flying a flight plan that no longer has a living crew able to interrupt it. Meanwhile, inside, the exact physiology described earlier runs its own separate countdown. Vision narrowing, coordination failing, then nothing at all. The parachutes deployed on schedule, the retro rockets fired on schedule. Recovery teams reached the capsule within minutes of landing, precisely where tracking said it would be. Every mechanical system aboard Soyuz 11 performed a technically flawless landing, precisely on target, right on time. The single fact investigators found hardest to sit with afterward: a spacecraft can do everything right and still come home carrying no survivors, because the failure that mattered took less than a minute, and every safeguard built into the mission was designed to catch something slower, the same margin that would decide your own outcome if you were ever the one strapped into that seat. Engineers rebuilding the failure afterward traced it to a design assumption nobody had thought to question. That separation shock would never be violent enough to jar a valve loose this early. That single, unexamined assumption, sitting untouched in a design document for years, turned out to be the entire chain's weakest link. Not a dramatic failure of imagination, but an ordinary one, the kind every complex machine carries somewhere inside it, waiting for the one specific sequence of events that finally finds it. Every crewed capsule since has carried a redesigned valve and pressure suits during launch and landing, specifically because a cascade this fast leaves no room for a second layer of protection to activate in time. The lesson written into hardware was simple, and cost more than any lesson should. Assume the shock will be worse than the engineers expect, because eventually, once, it always is. Strip away skin, muscle, every soft tissue already discussed tonight, and one part of the body remains stubbornly unbothered by almost everything vacuum can do to it: bone. Unlike soft tissue, bone carries very little of the water that ebulism and slow sublimation target first, and its mineral structure largely calcium phosphate, the same category of mineral that makes up a seashell or a piece of chalk, simply has nowhere near as much to lose. Radiation still reaches bone, but slowly, and its effects there are measured in centuries rather than months. Ultraviolet light barely penetrates beyond the surface at all. Micrometeorite impacts, covered later tonight, chip away at exposed material regardless of what it's made of. But bone resists that erosion measurably longer than soft tissue ever could, the same reason fossilized bone survives burial for millions of years, while skin and muscle vanish within decades even underground. Consider what that means for the order in which a body in vacuum would actually disappear, piece by piece, across a genuinely long span of time. Soft tissue first, freeze-dried and radiation-etched within years, connective tissue and cartilage next, over a longer stretch of decades, and bone, last of all, potentially persisting, structurally recognizable, for a span of time that makes every process already described look almost instantaneous by comparison. On Earth, bone survives burial specifically because the ground protects it from the very forces that damage it fastest. Oxygen, moisture, temperature swings, direct sunlight. Paleontologists rely on this constantly, pulling recognizable skeletal structure out of rock that formed millions of years after the animal died. The organic material long gone, replaced slowly by minerals seeping in from the surrounding stone. Space offers none of that slow, gentle mineral replacement. What it offers instead is simple absence. Nothing buried, nothing replacing it, nothing rushing in to fill the space soft tissue used to occupy. Bone in vacuum does not fossilize, it simply persists. Unburied, exposed the entire time, changing far more slowly than anything around it. Now multiply that resistance by the specific quiet of true vacuum, where there is no wind to sandblast a surface, no rain to dissolve mineral structure, no freeze-thaw cycle prying. Tiny cracks wider every winter, the way frost does to stone on Earth. Whatever finally wears bone away in space is a slower, stranger set of forces entirely. The same radiation and micrometeorite bombardment already introduced tonight, just acting on a material that resists both far longer than skin, muscle, or even the leathery, freeze-dried remnant of a mummified body ever could. This is not a comforting fact, and it is not meant to be one. It is simply what happens when a material built to survive on a geological timescale on Earth, buried, protected, slowly mineralizing into fossil over millions of years, is instead left directly exposed to space, with nothing burying it and nothing to interrupt the process at all. The last part of you to stop looking like you, in other words, would be the part that never looked most like you to begin with. So now we have the first real piece of the answer tonight's title actually asked for. About your own body specifically. It does not explode, does not freeze solid, and does not rot the way anything on Earth rots. It changes state instead, swelling briefly, losing its moisture within days, freeze-drying into something closer to parchment than to a corpse, while radiation and ultraviolet light begin a disassembly measured in years rather than hours, and while bone quietly outlasts everything softer than it. But on its own, this still proves only the first hour of a story that, left undisturbed, keeps unfolding for spans of time. Human minds were never built to intuitively hold. Everything covered so far, the seconds of consciousness, the boiling saliva, the freeze-dried skin, even Laika's 45-year hidden telemetry, even the 3 cosmonauts whose final minute rewrote a theory into documented fact, happened within a single day of the moment each body was first exposed. Consider, for a moment, how strange that actually is. An entire physiological emergency, complete from first symptom to final stillness, compresses into less time than most people spend commuting to work. And yet the object left behind by that emergency does not politely finish its story on the same short clock. It keeps existing, unattended, subject to forces that operate on a completely different scale of time than the ones that ended it. What comes next does not happen in hours or days at all. It happens across years, then centuries, then stretches of time so long that entire human civilizations could rise and vanish twice over before the story finishes. Picture it as a single upward staircase from here to the end of tonight. Minutes behind us now, years just ahead, then centuries, then millennia, then spans of time so large that millennia itself stops being a useful unit at all, and the single detail that decides how that longer staircase unfolds barely sounds scientific at all. Altitude, plainly measured in miles, mattering more to what comes next than the cause of death. or the condition of the tissue ever will. It alone decides whether a body's next chapter is measured in single years or in spans of time long enough to make years themselves feel like the wrong unit to even reach for. Think of altitude for a moment as the only real fork in this entire story. Every fact covered in the last hour applies identically no matter where your body ends up. The same 9 seconds, the same freeze-drying, the same slow radiation damage. But the instant your body settles into an orbit or drifts free of one entirely, its story splits into 2 completely different futures, and nothing about you gets any say in which one you receive. One version of that fork brings a body home again, burning. Within a span of time, a person could plausibly have lived to see out. The other releases it from any deadline at all, adrift on a path that may never again intersect a single planet, star, or living witness. Tonight walks both paths in turn, starting with the one that ends soonest. Space does not begin at one clean edge, the way a map might suggest. It begins as a thinning, a gradient, the atmosphere growing fainter and fainter without ever fully reaching zero, all the way out to hundreds of miles above the surface. That faint remainder matters more than its thinness implies, because it is still enough to drag against anything orbiting inside it, one nearly imperceptible collision of stray molecules at a time. Low Earth orbit the zone housing the International Space Station. Most satellites, and any human body released at a typical mission altitude, sits close enough to that thin remaining atmosphere to feel its drag constantly. Every object there is losing altitude, slowly, whether anyone notices or not. It simply takes long enough, at most of these altitudes, that the loss is invisible on any human timescale shorter than years. Climb higher, past roughly 12,000 miles, and the atmosphere's reach effectively ends. Medium Earth orbit, home to GPS satellites and geostationary orbit, roughly 22,000 miles up, both sit far beyond any meaningful drag at all. An object released there is not falling home in any span of time worth naming in years. It is simply staying, indefinitely, governed by gravity alone with nothing left to slow it down, and past Earth's gravity entirely, on a trajectory fast enough to escape it. An object stops orbiting anything at all. It becomes a tiny, independent traveler, subject only to the sun's gravity, and eventually, not even that. 3 futures then, decided entirely by one number set at the moment your body is exposed. A slow return within years, a near permanent stay lasting longer than human civilization, or an open road with no destination and no return. Tonight starts with the fastest of the 3. Picture the difference as 3 rooms in the same house, each with a different kind of door. The first room's door swings slowly shut on its own, over years, pulled by a draft too faint to feel. The second room's door is bolted, essentially permanently, by a lock with no key and no reason to ever turn. The third room has no door at all, only a hallway leading outward, with no wall anywhere to stop at. Engineers choosing an orbit for any real mission already think in these terms, though rarely frame this starkly. Every satellite launched carries, from the moment of design, an implicit answer to the same question tonight is asking about a body instead of a spacecraft. How long is this object meant to last, and what happens to it once its working life ends? Most of the time, nobody plans for the answer to include a person. Tonight, for a few minutes, it does. International guidelines actually require satellite operators to plan for this kind of ending in advance, mandating that spacecraft in low orbit be designed to re-enter within 25 years of the end of their mission, specifically to prevent the buildup of dead hardware circling indefinitely. No equivalent guideline exists for you, because no space agency on Earth has ever needed to write one. The International Space Station orbits roughly 250 miles up, and even there, in what counts as a stable working altitude for a permanently crewed spacecraft, atmospheric drag is strong enough that the station would fall out of orbit within a handful of years without regular engine boosts, pushing it back up. mission controllers perform those boosts routinely. A maintenance task few outside the space program ever think about, simply to keep humanity's most expensive orbiting laboratory from quietly falling back to Earth on its own schedule. Your body, far lighter and offering far less surface area for drag to act on than an entire station, would behave differently, but the underlying mechanism is identical. Gradual, cumulative loss of altitude, orbit after orbit. Each pass through the outermost wisps of atmosphere, shaving off a little more speed until the orbit finally collapses entirely, and you begin your final, fast descent into thicker air. That descent would not look like a landing at all. There would be no capsule, none of the careful heat-shielding engineering that brings astronauts home intact. Entering the atmosphere at orbital speed generates enormous heat through compression and friction against increasingly dense air. The same mechanism that turns a fist-sized meteoroid into a brilliant, brief streak of light every night somewhere over Earth. A body without any protective structure around it would very likely be almost entirely consumed by that heat. The same fate as the overwhelming majority of the debris that re-enters Earth's atmosphere every single year, unnoticed, over oceans and empty land. Sputnik 2 followed this same path in April of 1958, carrying Laika's body through re-entry a little over 5 months after launch, at an altitude low enough that atmospheric drag had done its patient work in months rather than centuries. Nothing about that re-entry was designed, controlled, or gentle. It was simply orbital decay, running its course, the same process that would apply, on a matching timeline, to any body left in a similarly low orbit today. Modern tracking networks confirm how often this happens without ceremony. Multiple pieces of tracked orbital debris burn up in Earth's atmosphere on an ordinary week, the vast majority disintegrating so completely, so far above any populated area, that nobody on the ground ever notices a thing. A handful of denser fragments occasionally survive the descent far enough to reach the ground intact. Dense metal components. Mostly chosen by the accident of their own construction, rather than any special protection. Your body, largely water and soft tissue, even after everything already lost to vacuum, would sit firmly on the side of that equation that does not survive. There is a specific, almost gentle irony buried in this fact. A body preserved so carefully by cold and dryness for years in orbit would meet its actual, final ending in the single hottest, most violent few minutes of its entire journey, turned, in the end, into the kind of brief, bright streak across the sky that inspired the wish so many people make looking upward, with no idea what they are actually watching burn. Move the same body up to geostationary altitude, and the entire timeline covered a moment ago stops applying almost completely. There is essentially no atmosphere left to drag against at that height, and the orbital decay that guarantees a return within years at lower altitudes simply has no mechanism to act through up there at all. Satellite operators know this well enough to have built an entire policy around it. Retired geostationary satellites, rather than being left in their working orbit indefinitely, are deliberately boosted a few hundred miles higher into what the industry plainly calls a graveyard orbit, a parking place for dead hardware, chosen specifically because almost nothing will disturb it again, for a span of time longer than any company or any civilization currently expects to exist. Estimates for how long an object remains in a stable high orbit like this run into the millions of years, limited less by any decay process and more by the slow, gravitational tugging of the moon and sun, nudging orbits very gradually out of their original shape over truly enormous stretches of time. Nothing dramatic ends it. No fire, no re-entry, nothing resembling a single clear finish. Just a stable path, holding almost perfectly steady, for longer than recorded history, has existed by a factor most people would need several tries to say out loud correctly. Released at this altitude, you would not return home burning within your own lifetime, or within 100 lifetimes stacked end to end. You would simply keep circling, changing slowly in every way already described. Freeze-dried, radiation etched, your softer tissue receding year by year, while the orbit itself barely moves at all. Consider what it would mean, concretely, to still be up there 1,000 years from now. Every language currently spoken on Earth would have drifted into forms unrecognizable to us tonight. The way Old English reads as a foreign tongue to modern speakers barely 1,000 years removed from it. Entire nations would rise, and very possibly fall, in the time it takes that single orbit to complete only a small fraction of its own, extremely gradual decay, and still, up there, something recognizably shaped like a person would keep circling overhead, changing more slowly than any single human institution ever has. Now combine that stability with everything already established about radiation and micrometeorite erosion, and a strange picture comes into focus. Not preservation in the comforting sense the word usually carries, but persistence. Continuing to exist, slowly reshaped, long after every reason anyone might have had to look for it has been forgotten by everyone who ever could have looked. Satellites left in these graveyard orbits today will, by most estimates, still be circling millions of years from now, long after the companies that launched them, and quite possibly the language used to name them, have vanished from any record at all. A body sharing that same orbit would share that same fate, indifferent to the passage of every human century sliding past beneath it. Space is not as empty of solid matter as its silence suggests. Tiny fragments of rock, ice, and metal, some no larger than a grain of salt, most far smaller than that, drift through every orbit at velocities easily exceeding 10 miles per second. Fast enough that even a speck weighing almost nothing carries the destructive energy of a fired bullet on impact. Engineers know this danger with unusual precision because they have retrieved the evidence firsthand. When the Hubble Space Telescope's original solar panels were replaced during a servicing mission and brought back to Earth for study, researchers found them peppered with thousands of tiny impact craters, each one the signature of a micrometeoroid or fleck of orbital debris striking at extreme speed over years of continuous exposure. Some craters measured only fractions of a millimeter across. Others had punched clean through multiple layers of material entirely. Your body, in a stable, long-lived orbit, would accumulate a version of that same bombardment, one imperceptible impact at a time, for as long as it remained exposed. No single strike would do anything dramatic. Most particles are simply too small to notice on contact, but across centuries, then millennia, then longer stretches still, the cumulative effect is a slow, granular erosion, sandblasting exposed surfaces, one microscopic collision after another, the same principle that pits the leading edge of any spacecraft that stays aloft long enough to measure it. Now consider what that erosion actually does to the freeze-dried, radiation-hardened remnant left behind by everything already covered. It does not carve anything dramatically. It simply, patiently removes material from the outside in, a fraction of a millimeter accumulating into measurable loss only after spans of time long enough that the erosion becomes the dominant force, reshaping whatever is left, more influential over the very long term than radiation, and far more influential than anything resembling decay. Spacecraft designers now build entire shielding systems around this exact threat, layering sacrificial material. Thin sheets designed specifically to absorb and vaporize an incoming impact before it reaches anything critical underneath. Around modules meant to remain in orbit for years, the technique works precisely because the threat is not one large, dramatic strike. It is thousands of tiny ones, arriving at random, each one individually survivable, each one collectively unavoidable across a long enough exposure. With no shielding of your own, you would simply absorb every one of those impacts directly. Over years, the effect would be barely perceptible. Over centuries, surface texture would visibly roughen, the way a stone left exposed on a windswept ridge slowly loses its polish. Grain by grain, without any single gust ever seeming responsible for the change. Over millennia, entire surface layers, already thinned by radiation and drained of moisture, would simply, gradually, cease to exist at all, not consumed by any dramatic event, but sanded away by a version of weather that never rests and never needs a storm to do its work. In 1991, hikers in the Alps found a human body preserved in glacial ice, later named Ötzi, dead for roughly 5,300 years before anyone laid eyes on him again. Cold and dryness had done what no embalmer ever could. Preserved skin, muscle, tattoos, even the contents of his stomach, intact enough for modern researchers to reconstruct his final meal, down to the type of grain he had eaten. Egyptian mummification, by comparison, required deliberate human effort, removing organs, packing bodies in salt, wrapping them in treated linen, an elaborate chemical and ceremonial process repeated over weeks. Ötzi received none of that. He simply froze, in a place dry and cold enough that decomposition never had the chance to begin, preserved by accident rather than designed for longer than Egypt's oldest pyramids have existed. Space offers a more extreme version of the very conditions that preserved Ötzi without even needing the ice. No liquid water survives long enough to freeze in the first place. It sublimates away directly into vacuum, faster than any glacier ever could. No bacteria arrived to attempt decomposition at all, not even briefly, the way a handful of hardy microbes may have lingered at the edges of Ötzi's icy tomb. A body in a sufficiently stable orbit would be drier, colder in its shadowed regions, and more completely isolated from any decomposing organism than any accident of terrestrial geography has ever managed to produce. The comparison is not close. Ötzi survived 5,000 years by good fortune, buried in precisely the right conditions completely by accident. A body in a high, stable orbit would face better preservation conditions than his, sustained not for thousands of years, but for a span of time long enough that well preserved stops being an adequate description of what's actually happening. Researchers who studied Ötzi's remains found something else worth holding on to. His body still carried traces of the last meal he ate, pollen from the plants blooming around him at the time of death, even the specific type of stone used in the tools he was carrying. 5,300 years of cold, dry storage had not erased the fine, specific details of an ordinary day. Only the life that had been living it, a body preserved in the emptier, drier, colder conditions of a stable orbit, would likely hold on to details with even greater fidelity, for a span of time long enough to make Ötzi's 5 millennia look, by comparison, like a body barely finished settling in. Whatever fine details a person carried at the moment of their exposure, the specific position of a hand, a fold in fabric, a last ordinary expression frozen mid-thought, space would be under no particular hurry to erase any of it. But there is an obvious difference between Ötzi and this hypothetical traveller that changes the entire meaning of the comparison. Ötzi was eventually found, studied, given back a kind of presence in the world he had been missing from for 5,000 years. A body in orbit carries no such guarantee. Preservation, without anyone ever coming to look, is simply a very long, very careful kind of disappearing. Every scenario walked through so far assumes a body still bound to Earth, orbiting, however slowly falling, or however stubbornly staying. There is a third path, and it removes the word orbit from the story entirely. A trajectory fast enough to escape Earth's gravity altogether, released outward on a path that simply never turns back. Humanity has already sent real objects down this same road. Voyager 1, launched in 1977, left our solar system's most meaningful boundary behind in 2012, and continues moving outward today at roughly 38,000 miles an hour, with no engine firing, no fuel spent, coasting on momentum alone through a medium with nothing left to slow it down. It will still be moving at that same speed long after every human institution that built it has changed beyond recognition or ceased to exist at all. Your body, on a comparable trajectory, would behave identically, obeying the same simple law. An object in motion, with nothing to act against it, stays in motion indefinitely, forever. No atmosphere to burn you up, no gravity well to eventually pull you back down, no micrometeorite bombardment intense enough over any span of time physics can currently describe to meaningfully alter your motion at all. But here is the part that never resolves and was never going to. Nobody knows what such a body would ultimately encounter, if anything, on a journey with no fixed destination and no scheduled end. The nearest star system lies years of travel away, even at enormous speed, and the odds of ever actually intersecting another star, another planet, another single point of interest across the emptiness between them are close enough to zero that unlikely undersells it. A body released this way is not traveling toward anything. It is simply continuing the same way it started for as long as there is anything left of it to continue as. Voyager 1 carries a golden record aboard it, a deliberate message for whatever, if anything, might one take day intersect its path. Sounds, images, greetings in dozens of languages, chosen carefully by scientists who understood exactly how unlikely it was that any of it would ever be received by anyone. It was an act of hope built directly into a machine that would otherwise be traveling in total silence forever, without any observer to notice what it carried. A human body on the same kind of trajectory carries nothing like that record along with it. Only the atoms themselves, arranged for a little while longer into a shape that once meant something before the same slow processes. Radiation, dust, the simple passage of enough time finished disassembling that shape entirely. Atom by atom, somewhere far beyond the reach of any telescope that could ever confirm it happened. Mission engineers who calculated Voyager's trajectory did so, knowing full well it would likely never be found by anyone or anything at all. They built the record anyway. An act of hope requiring no expectation of an audience. The same quiet defiance, in its own way, that drives an entire species to keep listening for signals from a universe that has never yet answered back. Step back for a moment from every version of this story and hold it next to the one alternative most people never think to compare it against. What actually happens to your body if it were left, instead, on the ground? On Earth, in ordinary open air, decomposition there moves fast, driven by bacteria, insects, and weather working in coordinated, ancient efficiency. Soft tissue is substantially gone within weeks. Skeletonization, in most climates, completes within a handful of years. Buried instead of exposed, a body returns its component atoms to the surrounding soil within a span of decades to a few centuries at the outside, swiftly, by any cosmic measure, rejoining the cycle of nutrients, feeding new plants, new animals, new generations of the same kind of life it once was. Set beside every timeline walked through so far, the contrast could not be sharper. Earth recycles a body in years. Space, in a stable orbit, can preserve one for a span of time long enough to make recycling sound almost absurdly premature by comparison. The very quality that seemed, an hour ago, like the strangest fact of the whole night, revealed now as simply a difference in how quickly each environment gets around to the same eventual task. There is something almost generous about Earth's speed. Looked at from this angle, buried in ordinary soil, you become, within a single human generation, the calcium in a new tree's roots, the nitrogen in next season's grass, the raw material quietly folded into whatever grows in the same patch of ground afterward. It does not wait. It gets back to work almost immediately, woven back into the visible, living world within a span of time short enough for grandchildren to stand, unknowingly, on the exact atoms their grandparent once was. Space offers no such reunion and no such speed. Held in a stable orbit, high above any biosphere, a body's atoms simply wait, inert, unclaimed by any living system, of no use to anything until an entirely different kind of ending eventually reaches them. It is not a better fate or a worse one. It is only a slower one, patient in a way nothing on Earth ever has the luxury of being, content to let the story rest here, drifting, for as long as anyone cares to imagine. Every gardener, every forest, every quiet compost heap on this planet is, in its own small way, running the fast version of this same process, constantly, without ceremony, every single day. Space simply runs the slow version instead. No less real, no less complete, just stretched across a timescale. Nothing alive has ever been built to witness from start to finish. Because, make no mistake, even Earth's fast, efficient recycling and space's slow, patient preservation are aimed, in the end, at the same destination. Every atom either environment ever touches was already borrowed, briefly, from somewhere far older than the body itself, and every path tonight has walked, however different their timelines, ends at the same return. That resting point was never the end, and it was never going to be. Every scenario walked through so far, the years-long burn of a low orbit, the millennia-long stillness of a high one, the endless drift of a body released entirely free, describes a different timeline for the exact same underlying fact. Nothing about a human body in space is ever destroyed in the sense that word usually implies. It is disassembled, slowly or quickly depending on altitude, into smaller and smaller pieces, each one still fully itself, still following the same physical laws it always did. Every one of those pieces, all the way down, is simply an atom, and atoms do not decay into nothing under any of the forces already walked through. Radiation breaks chemical bonds. Micrometeorites chip away surface material. Heat and re-entry can strip a structure down to its rawest components. None of it destroys a single atom. It only rearranges where those atoms sit and how tightly they hold on to each other. This is the detail worth carrying into everything that comes next. A body in space, on any timeline, in any orbit, is not disappearing from the universe. It is returning, atom by atom, to a state of being simply, anonymously present in it. Floating debris, drifting dust, eventually indistinguishable from the countless other fragments of matter already moving through the same vast, quiet space around it. None of them marked, none of them mourned, all of them still, technically, present. That shift changes the entire shape of the question tonight's title actually asked. What happens to your body assumes a body is the relevant unit the whole way through, something that starts whole and ends broken, destroyed, or gone. But an atom was never obligated to stay arranged as a body in the first place. It was only ever borrowed into that shape, briefly, and every process already walked through, however dramatic or however slow, is simply the borrowing coming due, and every one of those atoms has a much older story than the one it just finished living. Long before they were ever arranged into the shape of a person, they were something else entirely, forged under conditions no laboratory on Earth could ever fully replicate, conditions found nowhere on this planet, at any point in its entire history, and found only in the collapsing, furious core of a star. Every version of this episode's title, in other words, was already answered once before, billions of years before any human body existed to ask the question at all. What happens to your atoms in space is simply the second half of a process that began the first time they were ever assembled. And the beginning of that process is stranger, by a wide margin, than anything covered in the hour already behind us, and considerably more violent than anything a body itself will ever experience again, measured in temperatures no living thing could ever describe firsthand. Push the timeline out far enough, past every scenario already walked through, and even the largest, most permanent-seeming fixture in this entire story stops being permanent at all. In roughly 5 billion years, our sun will exhaust the hydrogen fuel currently keeping it stable, swelling into a red giant large enough to engulf Mercury, then Venus, and by most current models, Earth itself along with it. If you were still orbiting Earth at that point, still drifting, still freeze-dried, still slowly eroding under micrometeorite bombardment, you would meet your true final ending not through any of the processes already described, but simply by being swallowed, along with the entire planet you once called home, into the expanding outer layers of a dying star. A body on an escape trajectory, drifting free of the solar system entirely, would miss that particular ending. It would simply keep moving, indifferent to the fate of the star and planet it left behind, continuing outward through a galaxy that will look, 5 billion years from now, only subtly different from the one visible tonight. Scientists modeling this transition describe the sun's outer layers eventually expanding to somewhere near Earth's current orbit, though the exact boundary remains debated. Some models show Earth's orbit itself drifting slightly outward first, as the sun sheds mass and loosens its gravitational grip, buying our planet a temporary reprieve before the expanding star catches up regardless. Either way, the surface temperature here would already have made the question moot for billions of years before the engulfment itself arrived. Oceans boiled away, atmosphere stripped, long before any expanding star ever needed to finish the job directly. But here's the question that keeps astronomers from calling this an ending at all. The sun's death is not a tragedy for the atoms it once helped assemble into a human body. It is closer to a homecoming. Every heavy atom in that body, the calcium in bone, the iron in blood, the oxygen in every breath already discussed tonight, was built inside a star before our sun ever existed. When our own star finally finishes its life, it will simply be doing, to whatever atoms remain nearby, the exact same thing some earlier, older star already did to build them in the first place. Hold that alongside everything covered across every altitude and every timeline tonight. The years, the millennia, the endless drift, and a strange kind of symmetry appears, no matter which path a body's atoms take, fast or slow, burned in an atmosphere, or scattered across a billion years of vacuum. Every single one of them was already a veteran of this same kind of ending once before, long before it ever became part of anyone at all. Nothing walked through so far has actually reached that earlier chapter directly. It has only pointed toward it, again and again, the same way every road in this story eventually leads back to the same furnace, waiting patiently in the part of tonight still ahead of us. Rewind, for a moment, past every year and every century already walked through, past even the sun's own birth, to the specific, violent event that first assembled the atoms now sitting quietly in your body. None of it happened gently. None of it happened on Earth, or anywhere near it. Hydrogen and helium, the two lightest elements, formed within minutes of the universe's own beginning, filling almost all of existing space with almost nothing but the simplest possible atoms. Everything heavier than that. Every carbon atom in your skin, every drop of oxygen in your blood, had to be built afterward, one nuclear fusion reaction at a time. Inside the crushing pressure and heat of a star's core, stars spend their entire working lives fusing lighter elements into heavier ones, releasing the energy that becomes starlight in the process. A star like our sun manages hydrogen into helium, and, near the end of its life, helium into carbon and oxygen. But fusion has a hard ceiling. A wall even the largest stars cannot fuse their way past through ordinary burning alone. Iron. Building anything heavier than iron through fusion costs more energy than it releases. A one-way door that no star's core can walk back through, which means every atom in your body heavier than iron, every trace of gold, silver, platinum, uranium, anything sitting near the bottom of the periodic table, required something far more violent than an ordinary star quietly burning fuel. It required an actual explosion, or an actual collision, energetic enough to force those extra, expensive neutrons into place all at once, rather than earned slowly over a stellar lifetime. Consider the specific engineering problem this creates for the universe itself. Fusing hydrogen into helium releases energy, which is why stars can burn stably for billions of years without any outside intervention. Fusing elements heavier than iron does the opposite. It consumes more energy than it produces. An accounting problem. No star's core, however massive, can simply power through by burning longer or hotter. Something has to force the reaction anyway, spending energy rather than harvesting it, in a process fast enough and violent enough to outrun the ordinary economics governing everything a star does for the rest of its life. Picture the difference as two ways of building a structure. Fusion up to iron is like a construction project that pays for its own materials as it goes, each new floor funded by the last one. Building anything heavier is like adding floors that cost more than the entire building is worth. Something only an outside catastrophe, arriving all at once, could ever justify forcing through. Iron, in this sense, is not just an element. It is a kind of financial ceiling written directly into the physics of every star that has ever existed. The exact point where the universe's own bookkeeping stops rewarding a star for continuing to build. For decades, physicists suspected supernovae alone might account for all of it. The real answer, confirmed only recently and only directly, turned out to be stranger and involved an entirely different kind of catastrophe altogether. Our Sun is not, and was never, a first-generation star. It formed roughly 4.5 billion years ago out of a slowly collapsing cloud of gas and dust, a cloud already seeded, before the Sun ever ignited, with heavier elements cooked inside stars that had lived and died long before our own solar system existed at all. That detail alone means the iron currently circulating in your blood right now predates the Sun itself by a wide margin, older than the very star it now orbits underneath. Some earlier, unnamed star, somewhere in this galaxy, spent millions of years fusing lighter elements together in its core, built up a dense iron center. It could no longer fuse any further, and then, having exhausted its only remaining option, collapsed catastrophically under its own gravity and detonated as a supernova, flinging that iron, along with a wide range of other elements, out into the surrounding gas cloud that would, ages later, become the raw material for an entirely new star system. Astronomers can measure this history directly, comparing the exact ratios of different elements in the Sun and in meteorites against the known signatures left by different kinds of stellar explosions, essentially fingerprinting which ancient events contributed which ingredients to our specific solar neighborhood. The picture that emerges is not of one single ancestor star, but of many, each contributing a different piece of the periodic table before any of it ever became part of a planet, let alone a person. Meteorites turn out to be unusually good record keepers for this kind of forensic work, because many of them formed early in the solar system's history and have remained largely unchanged ever since, effectively frozen samples of the exact raw material the Sun and planets condensed from. Certain rare isotopes found inside them decay at known, fixed rates, letting researchers calculate not only what elements were present at the solar system's birth, but roughly how long before that birth the relevant supernovae must have occurred. Every one of those ancestor stars is long gone now, their names unrecorded because nobody existed yet to record them. Their only surviving legacy, the specific atoms they scattered outward before dying. You are, in a very real sense, standing on and made from the unclaimed inheritance of stars nobody will ever be able to name. An inheritance passed down with no ceremony and no records, nobody left alive to claim credit for it, folded into a body that will, in turn, one day pass its own share onward. But iron, however dramatic its supernova origin sounds, is still on the lighter side of what actually exists in your body. Gold, platinum, and the heaviest naturally occurring elements needed something even more extreme than a single star's death. And confirming what that was took physicists until remarkably recently to prove directly, rather than simply suspect, after decades of educated guessing about which cosmic event could possibly supply enough raw force to build them. On August 17th, 2017, gravitational wave detectors in the United States and Italy picked up a signal unlike anything recorded before. Two neutron stars, each one the collapsed, ultra-dense core of a long-dead star, spiraling into each other roughly 130 million light-years away, and finally colliding. Within minutes, observatories across every populated continent turned toward the same patch of sky, racing to catch the fading afterglow before it disappeared. More than 70 telescopes and instruments worldwide eventually contributed data to studying that single event. An unprecedented, coordinated scramble that astronomers still describe as one of the most exciting weeks of their careers, watching in close to real time as decades of theoretical prediction either would or wouldn't survive contact with an actual observation. It survived spectacularly. The afterglow's exact colors and how they faded over the following days matched, almost perfectly, a decades-old theoretical prediction for what a collision this violent should produce. An intense flood of neutrons forced rapidly into atomic nuclei, building heavy elements far too quickly for any single star's core to manage on its own. Researchers estimated that single collision alone produced a mass of gold and platinum many times heavier than the Earth itself, scattered outward into space in the space of just a few days. Scientists confirmed, for the first time with direct observational evidence rather than theoretical modeling alone, that neutron star collisions are a primary source of the universe's heaviest elements. The gold in a wedding ring, the platinum in a catalytic converter, quite possibly atoms sitting in your own body at this exact moment, forged in a collision between two collapsed stars, in a galaxy most people have never heard the name of, long before Earth had finished forming. Astronomer Edo Berger, one of the researchers who helped lead the rapid follow-up observations that August, later described the event as the moment decades of theoretical work about where heavy elements come from finally met an actual, undeniable answer in the sky. Teams that had spent entire careers building models of collisions nobody had ever directly observed suddenly had real data to check their equations against. And the equations held. Rarely does an entire scientific question resolve this cleanly, this quickly, in front of a global audience of researchers watching the same data arrive in real time. Most open questions in physics stay open for generations. This one, decades in the making, was answered within about a week of a single fortunate signal reaching Earth's detectors from an event that had already been over for 130 million years before anyone on Earth noticed it happened. Here's what almost nobody sits with long enough to feel the full weight of. That single, distant, violent event is not separate from your own body. It is, in a very literal sense, one of your body's actual origin stories. One chapter among several in a biography that started long before anything resembling a person existed to read it. Set the collisions and explosions aside for a moment and consider what all of it adds up to, sitting quietly in your body right now, tonight, as you listen to this. The calcium holding your bones together, the oxygen moving through your blood with every breath, the iron carrying that oxygen exactly where it needs to go. None of it originated on Earth. All of it was manufactured somewhere else first. Inside stars that finished burning long before our own sun ever existed, then scattered across the galaxy by explosions and collisions violent enough to still be studied by astronomers today. This is not a metaphor, and it is not a comforting turn of phrase invented to make a documentary feel meaningful. It is a measurable, physical fact, confirmed the same way any other chemistry is confirmed, by tracing which nuclear processes can produce which elements, and finding no other plausible source for the atoms making up your body besides the stars that came before it. Scientists sometimes reach for a specific, almost domestic number to bring the scale of this a little closer to graspable. The average adult human body contains roughly 7 billion atoms, and every single one heavier than hydrogen or helium has this same stellar origin. No exceptions. No alternate source anywhere in known physics. That number is too large to picture directly. What it means, practically, is that there is no part of your body, down to a single strand of hair, built from anything except recycled stellar material, assembled by gravity and chemistry into a shape that happens, for a while, to be able to wonder about its own ingredients. You are, at this exact moment, resting somewhere on Earth, made of matter that has already survived at least one supernova and an amount of gravitational collapse that would erase almost anything else in existence. Whatever this night has felt like so far, your own body is already a survivor of some of the most violent events the universe has ever produced. There is no test, no scan, no measurement that could ever separate the star part of your body from the you part, because there was never a meaningful line drawn between the two to begin with. The distinction only feels real because of how much time has passed, and how thoroughly gravity and chemistry did their work, rearranging the same raw material into something capable of listening to a story about itself. That is worth letting settle for the rest of tonight. Long after the specific facts about vacuum and orbits have faded, the line between star and person was never physical to begin with. It was only ever a matter of time and shape, and how patiently you were willing to trace the material backward. And it will survive one more, someday, whether that ending comes in a hospital bed, a quiet room, or, as tonight has spent the last hour exploring in careful, unflinching detail, in the vacuum of space itself, physics carries one law stubborn enough to apply to absolutely everything walked through so far. From the first 9 seconds of your own exposure to your body drifting for 1 billion years afterward, matter and energy cannot simply be destroyed. They can change form, change location, change temperature and state, almost without limit. But the total amount, measured carefully, never actually decreases. Every process tonight has described, however dramatic it sounded, was really just rearrangement, start to finish. Physicists call the underlying principle conservation, and it holds at every single scale examined tonight. Ebulism does not destroy water. It only changes it from liquid to vapor. Radiation does not destroy an atom's nucleus. It only knocks loose the electrons and bonds holding larger structures together. Even a supernova, however violent, does not erase the matter inside a dying star. It scatters that matter outward, unchanged in its fundamental accounting, ready to be gathered again into whatever comes next. Run the same lens back across every scene from earlier tonight, and the accounting holds without exception. Jim LeBlanc's boiling saliva didn't vanish. It became vapor, still present, still made of the same water molecules, just no longer liquid. The 3 cosmonauts' final breath didn't disappear into nothing. It simply mixed into the wider atmosphere of the capsule, and then, eventually, into the vacuum beyond it. Even Sputnik 2, burning on re-entry, converted its material into heat, light, and scattered particles, violent, visible, and complete, but never actually a subtraction from the universe's total ledger. Not one fact covered across this entire episode has actually described destruction in the strict physical sense of that word. Every single one of them, examined closely enough, matter or energy moving from one form, one place, one shape into another, following the same unbroken accounting the whole way through. There is a second law running alongside the first one, though, and it explains why none of this ever runs backward on its own. Entropy, the tendency of any closed system to drift, over time, from order toward disorder, from a small number of organized configurations toward the much larger number of disorganized ones. Your body is, among many other things, an extraordinarily improbable, extraordinarily organized arrangement of ordinary atoms. Vacuum, radiation, and time are simply very good at nudging that arrangement back toward the disorder it statistically prefers. Nothing about this is unique to space or to dying. It is the same principle explaining why a dropped glass shatters instead of reassembling itself, why a hot cup of coffee cools instead of spontaneously boiling on its own, why any organized structure, anywhere in the universe, eventually loses its shape unless something actively keeps rebuilding it. A living body spends its entire life fighting entropy, moment to moment, at enormous metabolic cost. The moment that fight stops, entropy simply resumes its default, patient work, on Earth, in the ground, within a matter of years, or in space, within a matter of orbits, centuries, or worse. Push entropy's patient work out past every timescale already walked through, past even the sun's death, past the death of every other star still burning anywhere in the galaxy, and physics arrives at a genuinely strange final question. One it has not yet fully answered. Does an atom itself last forever? Or does even matter, eventually, run out of road? Protons, the dense particles sitting at the center of every atom in your body, are assumed by most physicists to be extremely stable. But some theoretical models predict, instead, that protons might very slowly decay, breaking down into smaller particles over a span of time so long that the number describing it, a 1 followed by roughly 34 zeros, measured in years, barely functions as a number anymore, more a placeholder for longer than anything that has ever been measured directly. Experiments have run for decades, specifically trying to catch a single proton in the act of decaying, using enormous underground tanks of ultra-pure water, watched constantly for the faint flash of light a decaying proton would theoretically produce. So far, not one confirmed decay has ever been observed, in any experiment, anywhere. That absence has already ruled out some of the simplest theoretical models. It has not, and cannot yet, rule out the idea entirely. One of the largest of these detectors sits buried deep beneath a mountain in Japan, shielded by that enormous mass of solid rock, specifically to block out every other form of background radiation that might otherwise be mistaken for the signal researchers are actually hunting for. Scientists have watched tanks holding many thousands of tons of water, continuously, for years at a stretch, waiting for a single flash that would rewrite a fundamental assumption of physics. The current absence of any detection has already pushed the minimum possible lifetime of a proton, if it decays at all, out past 10 to the 34th power years. A number so far beyond the age of the universe itself that old stops being a meaningful description of it. Compare that number, for a moment, to every other span of time mentioned so far. The universe itself is roughly 14 billion years old. A proton's minimum possible lifetime, by current experimental limits, is already trillions upon trillions of times longer than that. If protons decay at all, they do it on a clock so patient that the entire history of stars, planets, and every human body that has ever existed would barely register as the very first tick of it. This is honestly unresolved. Not a gap in this episode's research, but a real, open question at the edge of physics itself. If protons do decay, then even the last scattered atoms of your own body, released into deep space and however perfectly preserved by cold and vacuum, would eventually stop being atoms at all, dissolving into the faintest possible particles and radiation spread so thin across an unimaginably vast universe that existing stops being a meaningful description of what remains. We still don't know which version of that far future is correct. And tonight, at the very edge of everything, physics can currently measure, that's where we have to leave it. Now, here's the reorganization that changes how almost everything already covered actually fits together. The title asked what would happen to your body in space. And for the better part of an hour, that felt like the right question. A question about explosions, about freezing, about rot, about one specific, bounded object, and what an environment might do to it. But a body was never really the fixed, stable unit this story kept assuming it was. It is, and always was, a temporary arrangement. Atoms borrowed from dead stars, assembled briefly into a shape capable of listening to this very sentence, and destined, on some timeline or another, to be unborrowed again. 9 seconds of consciousness, years of freeze-drying, millennia of orbital stillness, a final collision with an expanding sun, or an endless drift toward a heat-death physics still can't fully describe. Every single one of those was never really a fact about a body ending. It was a fact about atoms, briefly and improbably arranged, returning to the far larger, far older story they were only ever visiting from. This is why almost none of the questions this episode actually answered had a satisfying, final, and then it's over, waiting at the end of them. Freeze-drying doesn't end. It simply slows to a rate too gradual to watch. Orbital decay doesn't end. It simply transfers the story to a different kind of ending. Fire instead of stillness. Even the sun's death doesn't end anything. In the sense of stopping a process, it only changes which furnace is doing the reassembling. A question about endings, asked of a system that fundamentally doesn't do endings, was always going to produce an answer shaped like a chain instead of a period. Every fact covered tonight, reread this way, stops being a grim inventory of things that happen to a corpse and becomes something closer to a genealogy, a record of what a specific handful of atoms were doing before they were you, and what they will very likely be doing long after they no longer are. That reframing costs nothing in accuracy. Every physical detail from the last 2 hours stays true under it. It only changes which noun the story was actually about the entire time. Not a body, ending, but atoms, continuing, in a shape that happened, briefly, to include a body at all. Look back at everything covered tonight through that lens, and the whole shape of the episode rearranges itself. Jim LeBlanc's 14 seconds, Laika's hidden telemetry, the 3 cosmonauts whose autopsies confirmed a theory nobody wanted proven this way, Etsy's 5,000 years in the ice, a collision between 2 neutron stars 130 million light-years away. None of these were separate stories, loosely connected by a shared setting. They were the same story, told at different scales, about the same underlying fact. Nothing borrowed from a star was ever really yours to keep, and nothing borrowed from a star is ever actually lost. So here, finally, is the full answer tonight's title actually asked for. Not the first layer version covered an hour ago, but the complete one, assembled from every year, every century, and every billion-year span since. If you died in space, your body would not explode, would not freeze solid, would not rot the way anything on Earth rots. It would swell briefly, lose its moisture within days, freeze dry into something closer to parchment than to a corpse, drift for years or millennia depending on nothing more than altitude, erode slowly under radiation, and dust smaller than a grain of salt, and outlast almost everything soft about itself in the patient, mineral persistence of bone. And somewhere on a timeline measured in millions or billions of years, Whatever remained would finally rejoin the same furnace that built it in the first place. A supernova's expanding light, a dying star's final breath, or the slow, statistical dissolution of matter itself, at the very edge of what physics can currently describe. Every atom sitting in your body tonight was forged inside a star that died before our sun was even born. That was the very first thing this episode told you, 90 seconds in, before you had time to wonder why it mattered. It matters because it was never really an opening fact. It was the answer given early before the question had even finished being asked. Everything in between the 9 seconds, the boiling saliva, LeBlanc's chamber, Laika's hidden telemetry, 3 cosmonauts confirmed by autopsy, an orbit that either burns you home within years or holds you still for millions of them, a mummy in the ice, a collision between 2 dead stars 130 million light-years away was never a detour from that opening fact. It was the opening fact, unpacked, slowed down, shown from every angle, patient enough to actually look at it directly. A title asking what happens to your body was, this whole time, a title asking what a star's material does next, once it's finished being briefly, temporarily you. Tonight simply followed that material forward, honestly, through every timescale it takes to answer completely, from 9 seconds to 10 billion years, and every span of time in between. Nothing about you would explode. Nothing about you would be destroyed. You would simply return to the form you were borrowed from. Not erased, not lost, not gone in any sense that word usually implies, but released. Finally, back into the same vast, quiet, star-built material that was always, underneath everything else, what you were made of to begin with. That is not an ending in the way endings usually work. It is closer to the second half of a sentence that started billions of years before you were born, and that will keep being spoken, in one form or another, long after every trace of this specific arrangement has drifted back into the dark it came from. A sentence with no final period, only a very long pause between one shape and the next. None of this is closed, and none of it was ever meant to be. Physicists still don't agree on the exact fate of a proton. Nobody has ever recovered a human body from a truly long-term orbit to confirm, firsthand, how far freeze-drying and radiation would actually carry your own shape before it stops resembling anything at all. Every number offered across this episode is our best current answer, offered honestly, sitting right at the edge of what telescopes, autopsies, and gravitational wave detectors have actually been able to confirm so far. That openness is not a weakness in tonight's answer. It is the most honest thing about it. The universe is still being measured, still being questioned, still capable of surprising the very scientists who spend their careers trying to predict it. The same way a signal from 2 colliding neutron stars, 130 million light-years away, once arrived completely unannounced and rewrote what an entire field thought it already understood. Consider everything that had to go right just for tonight's episode to exist in its current form. Detectors sensitive enough to register a gravitational ripple, thinner than the width of a proton. A dog's 45-year-old telemetry, finally released by someone willing to admit the official story had been wrong. A technician's split-second decision to flood a test chamber faster than protocol allowed. None of these facts were guaranteed to survive into the present. Each one depended on somebody, somewhere, choosing curiosity over comfort and honesty over a simpler, tidier version of events. None of them arrived because the universe owed us an explanation. They arrived because specific people, at specific moments, decided a difficult truth was worth more than an easy one. The same quiet decision every scientist named tonight had to make at least once, usually at real, personal, or professional cost. Somewhere above you tonight, in an orbit nobody is currently tracking, in a supernova remnant still glowing faintly across the galaxy, in the quiet, patient math of an atom that may or may not ever decay, the same question this episode asked is still, technically, unresolved. And it will likely stay that way long after tonight ends. Long after this particular arrangement of atoms, listening to these words, has returned to whatever it returns to. There is something worth settling into, rather than resolving, in that fact. A universe that still has open questions, this large, this basic, is a universe still worth falling asleep underneath. Not because every answer is in, but because the searching itself never actually stopped and never asked anyone's permission to continue. It is an open question, still unresolved, still capable of surprising every physicist currently studying it, exactly as it was before tonight began. And just as it will still be tomorrow night, and every night after that, for as long as there is anyone left to keep asking, and quite possibly for a very long stretch of time after that too, long after the asking itself has been handed off to whatever comes next. Tonight, we drifted through a body's last 9 seconds, and through the billion years that came after them. We sat with a saliva boiling test chamber in 1965, with a dog's hidden telemetry, with 3 cosmonauts whose final minute confirmed a theory nobody wanted, proven this way. We climbed from low orbit to a graveyard orbit that will still be circling long after every name on this planet has been forgotten. And further still, out past the sun's own death, to a question about protons that physics has not yet finished asking. None of that was ever really about a body ending. It was about atoms, patiently returning to the vast and ancient material they were only ever borrowed from. The same star-forged calcium, the same star-forged iron, the same star-forged oxygen, moving now through you, tonight. You are not separate from any of this. You never were. The universe did not send you out into the world and lose track of you. It simply folded a small, temporary piece of itself into a shape that could wonder, for a while, what it was made of. And tonight, quietly, it wondered back. If your eyes feel heavy, let them close. There is nothing left tonight that needs you awake to receive it. If this felt like home, leave a comment when you wake up. The universe will still be here when you wake up. So will we. Good night.